The popular image of the early Earth is a sterile, fiery ball of magma, a planetary-scale version of Dante's Inferno. But the geochemical record tells a different story. Almost immediately after its formation, the planet began to organize. Look closely at this terrain. These are among the oldest surviving rock formations on Earth. Chemical signatures locked inside ancient crystals from similar early crust tell us that the surface had cooled enough to support liquid water oceans roughly 4.4 billion years ago, practically right after the planet formed. In those early oceans, microscopic biological engines came online. Microbes known as cyanobacteria were using sunlight to photosynthesize, pumping out oxygen gas as a waste product by at least 3.5 billion years ago. Biology began producing oxygen here as early as 3.5 billion years ago. Yet the gas didn't actually flood the atmosphere until 2.4 billion years ago. That's a billion-year gap in the geological record. If life was pumping out oxygen for an entire eon, why did the atmosphere remain toxic and anoxic? The early Earth faced a severe thermodynamic problem. 4 billion years ago, the sun was roughly 30% dimmer than it is today. Without an intervention, the entire planet should have frozen solid. The early Earth had an intensely hot interior, which drove a hyperactive system of volcanoes. These constant eruptions saved the planet by pumping enormous volumes of greenhouse gases into the air, creating a thick, insulating blanket. This atmosphere was heavily reliant on methane. Even in small amounts, methane is an incredibly potent greenhouse gas, trapping significantly more heat than carbon dioxide. While this methane-rich greenhouse system kept the oceans liquid, it also created a chemical environment designed to destroy free oxygen on contact. The early Earth was packed with sinks, vast reservoirs of chemicals that hunted and bonded with oxygen, neutralizing it the moment it was produced. The largest of these sinks was the ocean itself. The deep water contained no oxygen, but it was saturated with dissolved iron. As cyanobacteria released oxygen in the shallow waters, it reacted with that dissolved iron to create insoluble iron oxides, essentially rust. This rained down to the seafloor to form banded iron formations, easily identified by these distinct red and gray bands. The atmosphere acted as a second sink. Any oxygen molecule that managed to escape the ocean immediately collided with that thick blanket of methane. The two gases reacted, destroying both the methane and the oxygen. Simultaneously, a geochemical sink operated. Volcanic and hydrothermal vents released constant streams of reactive gases like hydrogen sulfide, which scrubbed whatever stray oxygen remained at the surface. Biology was a leaky faucet trying to fill an industrial drain. Oxygen couldn't accumulate because the entire chemical metabolism of the planet was engineered to consume every drop. Overcoming that bottleneck required a structural change to the Earth itself. Between 2.7 and 2.4 billion years ago, the planet's crust began to mature, establishing deeper, more efficient tectonic recycling. Cyanobacteria making oxygen also create organic carbon. If it decays, it consumes the oxygen back. But maturing tectonic plates dragged this organic waste deep underground. Locked away, it was removed from the equation. The oxygen was left behind, finally overwhelming the chemical drain. The smoking gun for this event is found in the rock record. A specific chemical fingerprint called S. Smith permanently vanishes from global sediments roughly 2.46 billion years ago. S. Smith is only created when harsh, deep ultraviolet radiation strikes sulfur in an oxygen-free atmosphere. Its disappearance proves that atmospheric oxygen finally reached a threshold high enough to form a rudimentary ozone layer, which blocked the radiation. The Great Oxidation Event happened because geology matured enough to store life's waste. But crossing that threshold did not create a sudden paradise. It triggered a near-fatal planetary catastrophe. As oxygen built up, it rapidly oxidized the atmosphere's methane greenhouse blanket, scrubbing it out of the sky. Stripping away that thermal insulation caused global temperatures to crash. Earth plunged into the Huronian glaciation, a planetary ice age lasting hundreds of millions of years. Simultaneously, this new reactive oxygen gas poisoned the existing anaerobic biosphere, causing Earth's first mass extinction. Achieving a breathable world for complex life wasn't a peaceful progression. It was the result of a violent planetary gamble, one where Earth's initial climate system had to crash and burn to make room for the next. We're used to measuring history in human terms. We map out empires, draw borders, and fight over coastlines, assuming the ground beneath our feet is a permanent, unshakable stage. We call it terra firma, solid Earth. Even when we try to look back into deep time, we usually stop at Pangaea. We treat it like the original map. But Pangaea is a late-stage arrival in a 4.5 billion-year-old planetary cycle. It existed for the last 5 to 10% of Earth's timeline, the season finale of a show that has been running since the planet formed. To actually map the ancient world, we have to look for cratons. Think of supercontinents as elaborate Lego castles. The cratons are the individual, indestructible Lego bricks. They are the ancient, rigid roots of a continent, light enough to float and strong enough to survive billions of years of planetary collisions. Because these cratons are so ancient, their bases go deep, plunging hundreds of kilometers into the mantle. They act as structural elevators, bringing precious materials up to the surface. When you see a diamond mine in northern Canada, you are looking at an elevator into a continental route that is nearly as old as the planet itself. Every border and city sits atop a temporary arrangement of ancient, wandering rocks. The solid ground we fight wars over is a passing configuration in a much longer story. The Earth's outer shell is broken into moving tectonic plates. Early on, the planet was a water world covered by oceanic crust. This rock is thin, but it's incredibly dense and heavy. When these plates crash into each other, the heavier one dives down, subducting back into the mantle to be destroyed. But a refining process happens in that heat. The heavy elements like iron stay down, while a chemically lighter magma rises to the surface and cools. This creates continental crust. It is too buoyant to sink, acting like a granite crouton floating in a sea of caramel. You can see the remnants of that early world today. This is oceanic crust, dense, heavy, dark basaltic rock. Compare that to the granite and andesite that build our continents. These lighter building blocks clump together to form the first permanent land. These land masses eventually create a pulse. As they crash together into a supercontinent, they act like a giant blanket, trapping the Earth's internal heat. That heat builds for millions of years until it rips the land apart from below. This cycle of assembly and violent heat-driven destruction is the primary engine of our planet. It is the force that dictated the air we breathed and forced all life on Earth to evolve. 2.7 billion years ago, the drifting cratons formed the first true supercontinent, Kenorland. It was a massive wall of barren rock that blocked global ocean currents, preventing the mixing of warm and cool waters. When Kenorland broke apart, it triggered a climate chain reaction called silicate weathering. This diagram shows how it works. CO2 from the air combines with rain to form acid, which reacts with the newly exposed rock and washes into the sea as sediment. This weathering process pulled so much CO2 out of the atmosphere that the planet lost its greenhouse blanket. Global temperatures plummeted to -50 degrees. Ice sheets a mile thick covered the entire surface, creating the first snowball Earth. Under the ice, a second crisis was brewing. Cyanobacteria were pumping out oxygen as a waste product. For the anaerobic microbes that ruled the world, this oxygen was a corrosive, deadly poison that burned them on a cellular level. We find the evidence of this pollution in these wavy layers of banded iron formations. It's a record of the ancient ocean literally rusting as it reacted to the new atmosphere. To survive this toxic world, life made a biological leap. One microbe engulfed another that figured out how to use oxygen as fuel. They formed a partnership. The smaller organism became the mitochondria, the cell's powerhouse. The climate collapse caused by Kenorland's breakup is the direct, singular reason the eukaryotic cell exists. Every plant and animal alive today is a descendant of that disaster. The Earth's rhythm continued through a stable, boring billion before assembling the next giant, Rodinia. History repeated itself. Rodinia trapped heat, ruptured, and triggered a second, even deeper snowball Earth. Environmental stress again pushed life to level up. When the ice finally thawed, the flood of nutrients into the ocean triggered the first explosion of macroscopic, multicellular animals. the bizarre, soft-bodied Ediacaran life forms. By the time the pieces formed Pangaea, the world was a scorching superdesert. Pangaea was so massive that rain clouds couldn't reach its interior, creating an environment of total extremes. Pangaea's existence contributed to the Permian extinction, a global volcanic crisis that nearly sterilized the planet. 96% of marine species disappeared. But by clearing the board, Pangaea's extreme geology forced the specific adaptations that allowed dinosaurs to conquer the land. The broken world it left behind became the cradle for a new era of life. We are currently living in a drift phase of this billion-year cycle. The Atlantic is widening, the Pacific is shrinking, and the plates continue to move at about the speed your fingernails grow. The pulse has not stopped. In roughly 250 million years, the continents will be pulled back together into a new megacontinent, Pangaea Proxima. When this collision happens, every border and coastline we recognize will be eradicated. In their place, the force of the plates will push up jagged mountain ranges that dwarf anything we see today. Our biology and our planet's geology are inseparable. We are the children of a climate disaster, living on rocks that refuse to stay still. Terra firma is foam floating on a boiling pot of magma, constantly rearranging and morphing. We are passengers on a very slow, very violent ride. Picture a standard 24-hour clock. Let that dial represent the entire 4.6 billion-year history of Earth, starting from the violent moment our planet formed at midnight, right up to the exact second you are watching this video. If you are looking for the historical landmarks we all know, you'll be waiting a while. Dinosaurs don't even show up until about 11 p.m. Humans? We are the final few seconds before midnight. We are practically a rounding error on this clock. Today, we are completely ignoring that final hour. We are going to look strictly at the first 23 hours. This is the Precambrian era. It covers roughly 88% of Earth's timeline. History books usually skip this era entirely because evidence is hard to find. Earth is a highly active planet. It constantly recycles its crust like a giant conveyor belt, pushing ancient rock deep underground and melting it back into magma. The library is constantly burning itself down. The chapters that did survive tell a violent story. Right out of the gate, Earth was slammed by a Mars-sized planet. The sheer energy of that impact vaporized massive portions of the rock itself, leaving behind a churning, toxic ocean of magma. For decades, geologists assumed the planet stayed a molten hellscape for hundreds of millions of years. But tiny, nearly indestructible crystals called zircons tell a different story. The chemical signatures trapped inside these microscopic time capsules show they formed in liquid water. Just 150 million years after the planet coalesced, the crust cooled enough for massive, high-pressure oceans to form. The oceans provided the physical medium, the hardware, but the atmosphere above it was incredibly dense and lethal. To build a world that could actually sustain complex organisms, biology had to write a brand new operating system from scratch. 4 billion years ago, the sun was roughly 30% dimmer than it is today. Based on standard astrophysics, a sun that weak should have left the early Earth completely frozen over. The planet stayed warm thanks to microscopic, single-celled organisms. These early microbes thrived in the oxygen-free oceans, and as they metabolized energy, they pumped out massive amounts of methane gas. Methane traps heat incredibly well, creating a powerful greenhouse effect. High in the atmosphere, that methane reacted with sunlight to form a thick, organic smog. If you looked up, the sky wasn't blue. It was a hazy, glowing orange. This blanket trapped the heat, and it acted as a chemical shield, blocking lethal ultraviolet radiation from reaching the surface. Life was keeping the planet perfectly warm. Then, cyanobacteria figured out how to use sunlight to split water molecules for energy. As they built the sticky, layered microbial communities we now see fossilized as stromatolites, they started releasing a highly reactive metabolic byproduct, free oxygen. The early oceans were packed with invisible dissolved iron. As soon as cyanobacteria puffed out a molecule of oxygen, it violently reacted with that iron, turning it into solid rust. For hundreds of millions of years, this iron oxide rained down to the ocean floor, forming the massive alternating bands of red iron and gray silica you see preserved in the rock record today. Eventually, the ocean's chemical sponge got full. With no more dissolved iron, free oxygen bubbled up and flooded the atmosphere. It immediately reacted with the methane blanket, stripping it away and replacing it with much weaker carbon dioxide. By pulling off the planet's heavy thermal blanket, this biological innovation poisoned its own environment and broke the planetary thermostat. The global temperature plummeted, and Earth plunged into its first snowball Earth event. Volcanic activity eventually built up enough greenhouse gas to melt the ice, leaving behind a brand new ozone layer. The planet stabilized, forming a single massive supercontinent. And then, for nearly a billion years, geology simply stopped doing anything interesting. This stability hindered evolution. The deep ocean layers became stagnant and packed with hydrogen sulfide gas. This sulfur bound tightly to trace metals like copper, zinc, and iron, pulling them down into the deep mud. The ocean ran out of the metallic building blocks needed to construct advanced enzymes, creating a nutritional plateau that lasted a billion years. Trapped in this nutritional wasteland, single-celled life turned inward. Simple cells swallowed other cells, forming permanent internal partnerships to generate energy. These complex eukaryotic cells eventually started shuffling their genetic code every generation through sexual reproduction, rapidly accelerating their ability to adapt to a harsh environment. Just as eukaryotic partnerships and sexual reproduction began rewriting the biological code, the stagnant supercontinent broke apart directly over the equator. Relentless tropical rain battered the newly exposed rock. This caused intense chemical weathering, a reaction that physically sucked carbon dioxide straight out of the atmosphere and locked it away in the ocean floor. The atmosphere lost its greenhouse heat once again. Ice caps formed at the poles. Because bright white ice reflects incoming sunlight rather than absorbing it, the cooling accelerated. The ice crept further and further down the latitudes until the entire planet snapped into a frozen, solid white sphere. Life was brutally compressed into tiny, disconnected safe zones near underwater volcanoes or slushy meltwater pools. This extreme geographic isolation acted as an evolutionary pressure cooker, forcing the survivors to adapt or die out entirely. Plate tectonics kept grinding under the ice. Volcanoes continuously pumping out carbon dioxide eventually overpowered the global ice. As the glaciers aggressively melted, they washed a massive fertilizer dump of rock dust into the oceans. This nutrient flush fueled incredible biological growth. The shallow seafloors were soon covered in thick, leathery microbial mats. Lying peacefully on top of these mats were huge, soft-bodied organisms absorbing nutrients right through their skin. No teeth, no hard shells, no predators. But a new type of animal was about to ruin the neighborhood. Symmetrical, worm-like organisms developed the musculature to aggressively dig down into the mud, rather than just politely sitting on the surface. This burrowing behavior shredded the fragile microbial mats. The flat, peaceful garden turned into a chaotic, three-dimensional mud pit. Animals started actively hunting each other, forcing prey to rapidly evolve hard calcium skeletons and defensive shells just to survive. Today, we look at the stars, hunting for Earth-like planets that might support biology. But for 88% of our own history, Earth-like meant a toxic orange smog or a ball of ice. We must realize that life is a geological force that engineered the blue sky we now take for granted. When you start a gas-powered car, the energy moving those pistons comes directly from the deep past. You are literally combusting the ghosts of a prehistoric world. The vast majority of the coal, oil, and natural gas we extract today was laid down during a specific block of deep time, the Paleozoic era. Between 541 and 252 million years ago, the Earth drafted the physical blueprints for our own bodies. Your spine, your jaw, and the limbs that carry you trace directly back to structural designs tested in these ancient waters. To understand the Earth we live on today, from the biology you see in the mirror to the climate crisis in the news, we have to look at how this ancient operating system was built and how it violently burned down. If you traveled back 541 million years to the start of the Cambrian period, you would likely be dead in minutes. You would find zero life on land, just bare, wind-swept rock. The air itself would suffocate you, holding only 5 to 10% oxygen. It was a deeply hostile environment, made even harsher by stellar evolution. The ancient sun was about 4 to 6% dimmer than it is today. Under normal conditions, the Earth should have been a frozen, solid ball of ice. What kept the water liquid was a massive greenhouse blanket. Carbon dioxide levels sat at over 3,000 parts per million. Complex animals weren't dropped into a ready-made paradise. They emerged onto a harsh, alien planet. And over millions of years, they would have to terraform it themselves. The laboratory for this early life was created by shifting tectonic plates. Global sea levels rose dramatically, spilling over the passive edges of the continents and flooding their interiors. These new shallow seas were warm, bathed in sunlight, and nutrient-rich. This perfect incubator triggered an evolutionary storm known as the Cambrian explosion. In a geologically brief window of perhaps 20 million years, nearly every major animal body plan appeared in the fossil record. Before this point, life consisted mostly of passive, soft-bodied organisms. Then, nature invented the predator. Creatures like Anomalocaris began hunting, which forced soft prey to pull calcium carbonate out of the water to build heavy armor. You can see the results of this biological arms race permanently etched in stone. These trilobites mineralized their bodies, spending massive amounts of metabolic energy on thick shells simply to avoid being eaten. The invention of the skeleton and the shell was essentially a biological military defense contract, shaping the fundamental anatomy of life. You have likely seen the famous illustration of a brave fish crawling onto dry land. Evolution doesn't plan ahead like that. Look at Acanthostega, an animal that lived 360 million years ago. It had 8-fingered hands, but it also retained internal gills, and its hips were far too weak to support its own weight out of the water. Limbs and fingers evolved entirely underwater to act as four-wheel drive for navigating dense, weed-choked swamps. This is known as exaptation. Evolution blindly hacked existing anatomy to solve an immediate underwater problem, accidentally building the precise biological tools that would allow animals to conquer the land millions of years later. While animals were navigating the swamps, terrestrial plants were engineering the climate. As they colonized the land, they evolved deep roots that secreted acids to chemically break down solid rock for nutrients. This rock weathering process acts like a planetary vacuum cleaner. It chemically pulls carbon dioxide out of the air, converts it into bicarbonate, and washes it down river systems into the ocean. By the Carboniferous period, terrestrial plants developed another major innovation: lignin. They grew tall, rigid trunks of solid wood. At the time, decomposers like fungi and bacteria hadn't yet evolved the enzymes to digest this new tough fiber. Because they couldn't be eaten, the dead trees didn't rot. Millions of generations of wood piled up in massive swamps, locking away their carbon. Global CO2 plummeted and oxygen levels shot past 25%. When we mine for coal today, we're hacking directly into these ancient, compressed layers of petrified wood that refuse to decay. Simple biological life had taken control of the climate system. By burying the greenhouse blanket deep underground, life engineered the cool, oxygen-rich world we eventually inherited. But 252 million years ago, this biological masterpiece was violently dismantled. The end Permian extinction, known as the Great Dying, wiped out 96% of marine species and 70% of terrestrial vertebrates. The trigger was a geological anomaly known as the Siberian Traps. This was an unrelenting flood of basalt that poured 1.5 million cubic kilometers of lava across the continent. The lava itself didn't destroy the biosphere. The catastrophe was a matter of horrific placement. The massive magma plume punched directly through underground basins packed with Paleozoic coal and salt deposits. The Earth had essentially drilled into its own massive buried fossil fuel reserve and set it on fire, converting a stable climate into a lethal greenhouse. This chart tracks the resulting geochemical kill chain. The burning coal injected massive volumes of CO2 directly into the atmosphere. Over a geological instant, global temperatures recorded a vertical spike of 8 degrees Celsius, subjecting land animals to fatal hyperthermia. As the atmosphere baked, the oceans absorbed the heat. Because hot water holds significantly less dissolved gas than cold water, marine circulation stalled. The oceans literally suffocated. Finally, the oceans absorbed the excess atmospheric carbon, turning the water into carbonic acid. Marine organisms couldn't build their skeletons. Their shells simply dissolved in the corrosive water. Breaching these specific geochemical thresholds triggered a cascading, multi-system planetary failure. When the dust settled, the diverse ecosystems were gone, and the Earth was temporarily inherited by fungi feeding on the dead. These are the mechanics of the Great Dying. A rapid injection of carbon dioxide, causing extreme warming, ocean deoxygenation, and severe acidification, are exactly what scientists track in our oceans and atmosphere today. When we extract these ancient deposits to fuel our power grids, we are unearthing the biological storage systems of the Paleozoic era and actively pumping that sequestered carbon back into the sky. Through heavy industry, humanity is replicating the chemical shock of the Siberian traps. We have become the flood basalt, manually triggering a rapid greenhouse event. But there is a crucial difference. A blind volcano cannot comprehend the data it leaves behind. We have the ability to read the rock record, recognize the limits of our biosphere, and choose to change course before we burn our own habitable world to the ground. When we picture the ancient world, we tend to rely on a cinematic snapshot, a giant reptile roaring in the rain, stomping through a misty, static jungle. Calling this 186 million year span the Age of Reptiles overlooks the actual story. We look at these isolated skeletons in museums and miss a larger, violently shifting stage they actually lived on. The Mesozoic involved the total reconstruction of the Earth's surface and atmosphere. The map was physically dismantled and rebuilt over millions of years. This era is an ancient laboratory. It is a nearly 200 million year experiment testing exactly what this planet is capable of when its physical systems are pushed to the absolute limit. 252 million years ago, every landmass formed a single C-shaped supercontinent called Pangaea, surrounded by one global ocean. Because of its massive size, ocean moisture couldn't reach the interior. Clouds dumped water at the coastlines, leaving the inner continent a vast desert. Pangaea was never going to last. Millions of years of volcanic activity physically tore the supercontinent apart, spewing massive lava flows that covered millions of square kilometers as the Atlantic Ocean began to unzip. As these colossal plates crashed, the crust buckled upward, forging the deep roots of massive structures like the Rocky Mountains, while simultaneously pumping staggering amounts of carbon dioxide into the atmosphere. The massive release of volcanic gas during this tectonic breakup cranked the planet's climate thermostat to extraordinary levels, forcing every living thing into a brutal survival test. This chart illustrates the sheer scale of the heat. While modern carbon dioxide levels are pushing past 420 parts per million, the mid-Cretaceous peak skyrocketed to 11 times that amount, wrapping the Earth in a thick, insulating greenhouse blanket. That heat deleted all permanent ice from the planet. Instead of frozen wastelands, the North and South Poles were covered in warm, dark, temperate rainforests where water temperatures neared 90 degrees Fahrenheit. When global ocean temperatures boil, normal circulation collapses. Cold polar water no longer sinks to drag vital oxygen downward. The deep oceans stagnate and suffocate into dead zones. Up in the hot shallows, delicate corals die off, replaced by resilient, box-shaped clams forming bizarre reefs. Extreme heat breaks the planet's core physical systems, dictating entirely new rules for who survives. On land, this extreme climate triggered a botanical transformation. For most of history, the world was dominated by ferns and conifers, until flowering plants suddenly exploded, an event Charles Darwin famously called an abominable mystery. This microscopic view reveals a mechanical breakthrough. Angiosperms evolved hyper-dense leaf vein networks, outclassing older plants. This better plumbing pulled water through stems faster, allowing them to keep surface pores open longer to suck in massive amounts of atmospheric carbon dioxide. By processing carbon at these speeds, flowers literally outgrew the slow-moving conifers. They dominated the upper canopy, stole the light, and rapidly diversified into thousands of species, entirely reshaping the dinosaur food web. Dominance in extreme climates is often won by superior natural engineering and hidden physiological efficiencies. The fossil record contains a diverse array of specialized mammals that lived alongside the dinosaurs, occupying roles far more complex than simple scavengers. There were semi-aquatic beaver-like swimmers, scratch diggers tearing into termite mounds, and species gliding between trees. A definitive find features a badger-sized mammal preserved with its last meal still intact. In its stomach region, paleontologists discovered the chewed-up bones of a juvenile dinosaur. This era was a diversity showcase for our ancestors. Mammals developed warm-bloodedness, grew large brains, and operated as active nocturnal predators in their own right. Life rapidly adapts to fill every available ecological role, regardless of which group currently sits at the top of the food chain. The dinosaurs did not end because of evolutionary failure. They thrived for 100 million years until a massive 10-kilometer rock violently interrupted the experiment. The Chicxulub asteroid impact filled the atmosphere with sulfur aerosols and ash, plunging the globe into darkness and instantly shutting down worldwide photosynthesis. Without plants, the food web collapsed from the bottom up. The specialized herbivores starved, followed by the massive carnivores. The survivors were adaptable scavengers who could hide in the dark and wait for the skies to clear. The very specializations that made the giants dominant in a stable greenhouse environment became their ultimate liability the moment the sun disappeared. This graph reveals a sobering modern parallel. The Mesozoic climate shifts took millions of years to unfold, but humanity is currently injecting carbon dioxide into the atmosphere 100 to 200 times faster than natural post-ice age cycles. The rock record offers a direct physical forecast. We know exactly what happens to the ocean when massive amounts of carbon enter the system rapidly, sweeping acidification, oxygen depletion, and the collapse of delicate ecosystems. Our position at the top of the food chain is not a permanent fixture. Mammalian dominance relies entirely on the random cosmic chance of an asteroid clearing the board 66 million years ago. We are fragile occupants, currently running a deadly, vastly accelerated version of an experiment the Earth already ran 186 million years ago. We tend to look at the history of life on Earth like a blockbuster movie franchise, where the dinosaurs were the perfect first film. They had the size, the teeth, and a 100-million-year run that ended when the asteroid hit. In reality, the 66 million years that followed, the Cenozoic era, are where the plot becomes incredibly complicated. The planet's stage underwent a period of physical demolition and reconstruction. The KPG extinction event wiped out the non-avian dinosaurs, the pterosaurs, and the massive marine reptiles. This created an ecological vacuum, a bustling world where the consumers, the movers, and the apex predators vanished overnight, leaving the food web in a state of collapse. Surviving life responded to this void with extreme aggression. In North America, the number of mammal species doubled within 100,000 years as life rushed to fill the empty hierarchy. The mammals that survived the asteroid were small, nocturnal creatures. Yet their body mass tripled in just 300,000 years. This rapid growth requires immense fuel, but the post-apocalyptic landscape offered little more than low-calorie ferns and scrub. The fossil record shows a solution appearing 700,000 years after the impact, the legume family. These plants evolved a relationship with bacteria in their roots that allowed them to fix nitrogen directly from the air, creating a built-in fertilizer factory that packed seeds and leaves with protein. These high-density botanical energy drinks provided the nutritional raw material for mammals to grow. With more protein available per bite, surviving lineages could specialize and rapidly scale up to conquer the land. 56 million years ago, the planet experienced a massive global warming event called the PETM. Forensic analysis of carbon isotopes points to a methane burp, the destabilization of frozen gas on the ocean floor, which injected over 2,000 gigatons of carbon into the atmosphere. Global temperatures rose 5 to 8 degrees, creating tropical dead zones, while crocodiles inhabited the Arctic. Acidic oceans dissolved seafloor shells. Mammals adapted via the Lillicrot effect. Early horses shrank 30%, coping with low-calorie, high-sugar plants. This shift in the fossil record suggests a link between the atmosphere's chemistry and the physical dimensions of the animals forced to survive within it. The Earth's cooling was driven by the movement of the continents. Roughly 50 million years ago, the Indian plate began a slow-motion collision with Asia, pushing up the Himalayas and the Tibetan Plateau. These mountains acted as a thermostat. Rain absorbed CO2, became acidic, and reacted with rock, scrubbing carbon from the air. Washed into the sea, marine life built shells, forming limestone layers that bears atmospheric carbon for millions of years. A second tectonic shift occurred at the bottom of the world. Antarctica physically separated from South America and Australia, opening new ocean gateways. This allowed the Antarctic Circumpolar Current to form, an uninterrupted loop of water that thermally isolated the continent. This current acted as a barrier, preventing warm tropical water from reaching the pole and locking Antarctica into a deep freeze. The movement of rock and the rerouting of oceans demonstrate that geography is the primary master of the global climate system. 34 million years ago, CO2 levels dropped past a critical tipping point. This triggered the explosive growth of continental ice sheets on Antarctica and shifted the Earth from a greenhouse state to an icehouse. In Europe, lush tropical jungles died out and were replaced by temperate woodlands and open plains, forcing a massive extinction of archaic mammals that were specialized for a soft, wet life. As the world became drier and lower in CO2, C4 grasses began to aggressively dominate the landscape, thriving while other ancient plants struggled. They used a specialized photosynthetic pathway to physically concentrate and hoard carbon dioxide inside their leaves. Eating these grasses introduced a survival challenge, grit. On windy, dusty plains, herbivores constantly ingested environmental sand and dirt along with their food. This drove the evolution of tall, self-renewing teeth in horses and other grazers to withstand a lifetime of mechanical abrasion. The cooling planet forced life to become tougher. Ruminants evolved complex internal fermentation tanks to digest fibrous forage, and herbivores developed specialized anatomy just to extract calories from a harsher, grittier landscape. 3 million years ago, the Central American Seaway closed, forming the Isthmus of Panama, blocking the flow of water between the Atlantic and Pacific Oceans. This closure forced warm tropical water to deflect north through the Gulf Stream. This change in circulation brought immense amounts of moisture to the high northern latitudes. The moisture provided the fuel for heavy snows. As the snow accumulated, it triggered an albedo feedback loop, where the white surface reflected sunlight back into space, cooling the region and helping to build the massive northern ice sheets. The resulting disruption to marine currents is linked to the extinction of ancient predators like megalodon. This cleared the way for modern, cold-adapted whales to flourish in the newly established, nutrient-rich currents of the cooling oceans. The closure of a single tropical gateway contributed to a climate feedback loop, providing moisture necessary for the ice ages that define our modern world. We now live in the Quaternary period, a time where the climate pulses between deep freezes and rapid thaws. This metronome is dictated by the Milankovitch cycles, subtle wobbles in the Earth's orbit and tilt. The variability selection hypothesis suggests that the rise of upright hominins was a response to this instability. Rather than evolving for one specific environment, early humans developed massive brains and tool use to survive a world that was constantly breaking and changing. We became specialists in handling climate chaos. Our intelligence developed as a survival strategy within the context of a fluctuating icehouse climate. Modern civilization is built upon the temporary stability of an interglacial pause. We rely on a climate that has, for a few thousand years, stopped its violent swinging. But we are currently releasing carbon at a rate comparable to the PETM warming event. We are pushing the atmosphere back toward a greenhouse state at a speed the biosphere has rarely seen. This brings us to the concept of hysteresis, that once a climate system is pushed past a chemical threshold, it can flip into a new state that is incredibly difficult to reverse. The 66 million year cascade shows that the biosphere always finds a way to adapt to a new normal. The question is whether our capacity for solving survival problems will be enough to navigate the cascade we have triggered.